Assalamualaikum and a very good morning. We are from Group 20. Today we are going to present our control system project, which is the Seismic Vibration Control System using tuned mass damper. Stay tuned to know more about our project. Today I'll be explaining how a seismic vibration control system works, focusing on its mass spring damper setup and PID controller. Imagine an earthquake causing ground movement. In this system, a mass represents part of the building or structure that experiences the seismic force. When the ground shakes, the mass moves, triggering the system's spring and dampers. The springs act as a restoring force, trying to bring the mass back to its original position, while the dampers dissipate the energy, reducing unwanted oscillations. But to actively minimize the vibrations, we need more than just passive elements. This is where the PID controller plays a crucial role. It continuously monitors the mass position in real time and applies corrective forces to counteract the vibrations.
This slide shows the block diagram and transfer function for the open loop control system. In open loop system, there is no feedback mechanism. The system operates based on the predefined inputs without considering the actual output. In the context of our seismic vibration control system, this means that the building structure will react to seismic force purely based on its inherent physical properties, without any active adjustment to reduce the vibration. The open loop transfer function was obtained for manual calculation and MATLAB simulation. This transfer function describes how the system responds to seismic vibration without any control. In the open loop configuration, we observe that high oscillation and long settling time, which indicates that the building experiences significant vibration and takes a long time to return to a stable state after the earthquake. In a closed-loop system, we introduce a feedback mechanism that continuously monitors the output and adjusts the control input accordingly. For the system, we use a PID controller to regulate the vibrations and reduce the oscillations. The closed-loop transfer function with the PID controller has been obtained using the MATLAB simulation. The transfer function shows that how the PID controller works to modify the system response by adjusting the proportional, integral, and derivative terms. The closed-loop system has improved stability with reduced oscillations and faster settling point, make it much more effective at managing seismic disturbance. The concept of PID controller. The PID controller plays a critical role in minimizing the building vibration during seismic event. It helps stabilize the building by continuously adjusting the control force applied by the tuned mass damper, ensuring the building returns to its equilibrium state as quickly as possible after being disturbed by seismic force. The PID controller uses three key components, which is proportional, integral, and derivative, which works together to reduce the building displacement, oscillation, and steady-state error. The proportional control generates a corrective force based on the current displacement of the building from its desired stable position. The larger the displacement caused by the seismic activity, the larger the corrective force applied by the TMD to reduce that displacement. The integral control addresses the cumulative displacement over time. After an earthquake, even a small displacement that aren't corrected by proportional control can cause the building to keep swaying. The integral terms help eliminate any steady-state error, ensuring that the building eventually settles into its original position. The derivative control predicts a future vibration by considering the rate of change of the building displacement. By using the rate of change of displacement, derivative controls helps to dampen oscillation that could arise due to the seismic forces, preventing the building from overshooting its stable position.
Next, I will explain about the step response. Firstly, open loop step response. The system shows natural response of the building structure to a seismic disturbance without any control applied. The step response represents the building displacement over time due to a sudden force. Next, for the MATLAB result, the open loop step response typically shows high oscillations and a long settling time, meaning the building sways back and forth for an extended period before coming to rest. Overshoot may occur where the displacement exceeds the equilibrium point, indicating instability in the structure response to seismic force. Secondly, closed-loop step response with PID. When PID controller were applied to the system, the closed-loop step response demonstrates how the controller helps stabilize the structure by minimizing oscillations and reducing settling time. For MATLAB results, firstly, it reduces overshoot. The displacement quickly returns to near zero or a stable point without swinging too far. Next, faster settling time. The vibration diminishes much more rapidly compared to the open loop response. Lastly, minimal residual vibrations. The building movement after seismic forces is significantly reduced, making it safer during and after an earthquake.
Let's talk about open loop stability in the seismic control system. In an open loop setup, where there is no feedback, the system's poles are closer to the imaginary axis. This means it has low damping and may oscillate, making it less stable without control. The system cannot effectively handle seismic vibrations and is likely to experience prolonged oscillations. Compared to the closed loop stability with PID control on the seismic vibration system, with the added of a PID controller, we see a significant improvement in stability. The poles of the system move further to the left in the complex plane, which means the system can dampen vibrations faster and reduce oscillations more effectively.
In conclusion, the seismic vibration control system with tuned mesh damper, TMD, and PID controller effectively improve the building response to the seismic event. In the open loop system, the step response reveals the slow recovery, high oscillations, and a long settling time, representing how the building would sway during and after seismic disturbance. However, in the closed loop system with PID control, the performance significantly improved. The PID controller reduced the overshoot, shortened the settling time, and minimized the residual vibration, resulting in much more stable structure. The pole zero map further illustrates that the PID controller moved the system poles to the more stable region, allowing the system to handle seismic force with the less oscillation and greater control. By carefully tuning the proportional, integral, and derivative component, the PID controller helps to reduce errors and vibration amplitudes, ensure a safer and more stable building response during seismic activity, ultimately reduce the risk of structural damage. Here is the reference for the MATLAB simulation coding. That's all from us. Thank you.